So we continue with the second section, projective and inductive limits. This should be a familiar algebra section. So let's go quickly through it. The notion projective respectively inductive limit generalize the operations of intersection and union. So the category of set, the intersection and the union can be realized as an inductive limit. Realize a projective limit and inductive limit. If there is a given family of subset of topological space X, which for any two set their intersection is still in this set, then the projective limit of this family is simply defined by this is the category of topological space. And we have to tile the transition morphism by inclusion. Remark that continued intersection should have a special name for this directed system. Usually it's called filtered, if I'm not wrong. In the case at hand, such a case is given by here we are defining what is a directed system. The directed system is an ordered set in which for every pair Ig there exists a k such that k is bigger equal than both of them. In the case at hand, such a k is given by intersection. Okay, that's what we said. There exists for any two topological subsets xi and xg, their intersection is also there. This amounts to, say, for an ordered set for any two element I and j, there exists the key which is bigger or equal to both of them. And for transition morphism, it is Fij, but in this special case is inclusion. Now we have to generalize this inclusion map with arbitrary maps. Let I be a directed system, a projective, respectively an inductive system. For I is a family of topological spaces. With objects and morphisms. Which satisfy the condition making diagram commutes. In order to define the projective and inductive limit of projective or inductive system, we make use of the direct product and disjoint union. Notice that here is always in the category of topological spaces. So the morphism of continuous maps. We're restricting ourselves in this category. So definition: the projective limit of projective system is defined to be the subset of the product of topological space. So it should be, as I said, the product of set, and the topology is the product topology. So there are tuples that satisfy certain rule, which means that if you know xg, you know all xi I less equals than g, which means that if you know xg in a couple of elements inside the inverse limit, let's suppose this is an element in the inverse limit. If you know xg, you know all the frontal element by this formula. Okay, it's clear. In more general, you know what are the elements before it. The product is equipped with product topology if the xi are Hausdorff, then so is the product, and it contains, in this case, x as a closed subspace. They can show that. This inverse limit or projective limit is a closed subspace of the top product. The projective limit of non-empty compact spaces is itself non-empty and compact. So the projective limit of compact is again compact. There are some properties we go through with it. The inductive limit, so now we are defining inductive limit of an inductive system, is defined to be the quotient of disjoint union. So you have to know disjoint union here is again a topological space. You have to know, as I said, how is it, and the topology, how is it. And then you quotient by the equivalent relation. The equivalent relation is telling that if they're finally equal, the direction is going to the limits following this direction of the arrow. In this case, it's the direction of the arrow is less equal. Is the arrow. And then if you coincide on far, if you meet in the far, that means you have two the same. More precisely, let's look at the Wikipedia for disjoint union topological space. In general topology and the related areas of mathematics, the disjoint union, also called direct sum, free union, free sum, topological sum, or coproduct, or a family of topological space, is a space formed by equipping the disjoint union of the underlying sets with a natural topology called the disjoint union topology. Roughly speaking, two or more spaces may be considered together, each looking at it would alone. The name coproduct originates from the fact that The disjoint union is the categorical dual of the product space construction. Which means that in the category, product and coproduct, as we know, they are a joint pair, right? So what should we write? What we have is what we have should be right, thing like this, and should be like this. That's what we know. In some category, like in category of modules, in some reasonable category, company category, for example. Suppose we have this, but this is not telling us product and coproduct. The joint pair, of course not. This is just telling you that yes, they are just due to each other, which means that the product category, say, is the coproduct of the opposite category. If you want, let's see what is categorical dual. In category theory of branching mathematical duality is correspondence between the properties of a category C and the dual properties of the opposite category. Give a statement regarding the category C by interchanging the source and target of each morphism as well as interchanging the order of composing two morphisms. A corresponding dual statement is obtained regarding the opposite category C of duality. As such, is the assertion that truth is invariant under this operational statement. In other words, if a statement is true about C, then its dual statement is true about C of. So statement about product is true for C, then the statement about coproduct is true for C of. Also, if a statement is false about C, then it still has to be false about C of. Okay, so I think it's enough. That's what we want. So we come back. Now let's define the disjoint union of a topological space. Let xi, x index by big I, be a family of topological spaces. Let x be the disjoint union of the underlying set. What is it? What is the disjoint union of underlying set? The disjoint union of a family of sets is a set. That's important. The disjoint union, so it's coproduct in the category of set. So you have to you have to say in the category discussing whether coproduct exists. If it exists, then this joint union exists because it's a special coproduct. In the category set, the coproduct is again a set with an injective function, which ai into a such that the union of this image of this injection form a partition of a. Otherwise, you can define the set. You can define it very naively, but in general, you should define it using universal property, n'est-ce pas? With an injective function which ai into a such that the union of the image of these injections form a partition of a, that is, each element of it belongs to exactly one of these images. The disjoint union family of pairwise disjoint set is their set union. Yes, for the pairwise set. Disjoint, yes. In terms of category theory, disjoint union is the coproduct of the category of set. A standard way of building disjoint union is to define the set of ordered pairs such that existing ai and the injective functions ai to a by x map to xi, and so to distinguish two set no matter the of intersection or not. So you have to give one more index to distinguish to embed into a bigger set with the injection map. So as a set, it is the disjoint union of set. As that we have to define topology now. Okay, so we give an injection for each set. Canonical injection. The disjoint union topology is defined the finite topology on X. The set which all the canonical injections are continuous. Explicitly, the disjoint union topology can be described and follows: a subset U of X is open in X if and only if its pre-image is open in X. Yet another formulation that a subset V of X is open relative to X if and only if its intersection with Xi is open for each I. Because at this moment you have topology for xi, you want to define topology for x. It's the same Miller as when we define the quotient topology. As we define the open here, it depends on the topology here. So we define the open to be those its intersection with xi are open for all I. When we define this way, then we find okay, phi I is a continuous. That is the finest one. Because when you define too many open here, there is a problem. But you define fewer open here, there is no problem. That's why we see this finest one. Make this work, okay? So now let GIG be projective and inductive system of topological groups. And the projective respectively inductive limit is a topological group as well. The multiplication, the projective limit is induced by the component-wise multiplication in the product, because as we said, it's a closed subset of the product. We have saw that, right? Product. Now saw that this is a closed subspace. So just induce the multiplication from there. In the case of inductive limits given to equivalence classes, I have to choose representative xk and yk in the same gk. in order to define xy to be the equivalent classes of their multiplication. And we have to check this is independent of the choice of representative. This is x, give y, that is, say we define to be. The problem is this is only equivalent classes, which means that there may be xi primes or g primes that are equivalent, so you have to check it's independent of the choice of representative. And then we have the projection. And then we have projections, inclusions. This is a universal property for projective and the inverse limit. Now we define what is morphism of two projective system. It is a family of continuous homomorphism. So this is the system. Morphism of the system. This is a system. This is another system, and the morphism between system is a family of continuous homomorphism making diagram commutes. Okay. Given two morphisms between inductive system and topological groups, such that for each I, every I, there is a exact sequence, then this is also exact. Okay. Actually, we haven't really defined what is exact for inductive and for induced sequence. But actually this is only object in the category of topological space, so these are topological spaces themselves. So of course you can check whether the kernel equals image and so on. Okay. The projective limit is not exact in complete generality, but only for compact groups. I think maybe we look at this proof. It's helpful. Let G prime be the inductive limit of Gi prime, and G inductive limit of Gi. G double prime is the inductive limit of G double prime I. We consider the commuted diagram. Now we choose x in G such that beta x equals 1. We have to check whether the kernel equals the image. And there exists an I and xi and xj such that it's because each one is it's because each one is exact by the assumption. I don't understand this. I don't understand this diagram, which means that the truth element here, this is xi, okay, which is mapped to 1. In particular, there exists an I and the xi in Gi such that yes, this is the definition of x. X by definition is xi. We have the morphism here. And the Gi double prime, so it's here. Okay. The Gi double prime beta I xi equals beta Gi xi, something here, right? The image here is mapped to 0. Put a star here, it's difficult. Okay, there exists G bigger equal than I such that beta I xi. This is beta I equals 1 in G prime. Why this is true? Because in the limit it is 1, which means when the index becomes bigger enough, it is 1. Or in other words, you can think about this. So this element is, of course, it's equivalent to I1. So any element that is mapped, so any element that is equivalent to 1, finally it must be mapped to 1 for some bigger index to GK. That's what it's saying. Changing notation, we may therefore assume that beta I xi equals I. So we must assume without changing representative, this is already 1, and so that there exists some yi is mapped to xi. By this we define all the yi, and hence we define element y or g prime. We notice that the image of this y is x. So that's a typical proof of dealing with projective in the projective limit and the inductive limit. This is just the key point is just to knowing that when you're discussing an element in truncation level gi, it's always up to equivalence. So you only have to add one more sentence saying that up to changing the notation, there is always a bigger index. Because there is always a bigger index, the one that we can do this. In this case is the special element that is equivalent to identity. Otherwise, you say we can change I to k to make all this work. And to make the image of gk under gk, yk mapped to y under gk. The projective limit is not exact in complete generality, but only for compact groups, so that we have the proposition that alpha and beta be morphisms between projective systems of compact topological groups, such that the sequences is exact for every I. Then the projective limit is again an exact sequence of compact topological groups. Did you see what's the difference? What we talk here is for inductive limit. You can see this is what? This is an exact functor. But in which category? Here is in the category topological space. And it's true in most category, I think. Usually we say projective limit is an exact functor. But for projective limit, it's not true. For compact ones, it's true. This is true. Or usually we say it's true and it has satisfied meta-level condition, right? Now that we have at our disposal the notion projective limit, we return to our starting point, the profinite groups. Recall that these are the topological groups which is hostile for compact totally disconnected. So the ultimate basis of neighborhoods of neutral element consisting of normal subgroups. The next proposition shows that they're precisely the projective limit of finite groups, which you view as compact topological groups with respect to the discrete topology. If G is profinite group and if ny is over the open normal subgroup of G, then one has algebraically as well as topologically isomorphism. Conversely, this is a projective system of finite groups. Then its projective limit is profinite group. So every profinite group can be written as the projective limit of finite groups. And projective limit of finite groups is again always is conversely always profinite group. Let us now illustrate the notion profinite group and projective limit by a few concrete examples. The Galois group This is what we have solved before in the first section when we established this. The transitional morphism is by doing the quotient. Yes, we have solved this. This is a typical example. Let's see the example 3. At the orbit valuation ring, the OK p-adic number field is local field, and so for Nokia p-adic number field is what we usually call local field. And let P denote the maximal ideal. The ideals, power of P, mix up a basis of neighborhoods of 0. OK is a Hausdorff compactness, so it's profinite ring. So it's a ring, and as a group it's profinite, so it's called profinite ring. The rings are finite. We have topological isomorphism. The group of units is closed, so it's Hausdorff compact. Closed of Hausdorff compact is again compact, and Hausdorff, of course, it's preserved by any subset, and this subgroup form a basis of neighborhoods 1U. Okay, this form a basis of neighborhood 1 inside the OK star. Really, we write this as the maximal ideas, like this. A basis of neighborhood. Is also profinite group. In fact, we have seen all this already in chapter before. Okay, we always see this also. Puffer ring. The ring is going to occupy quite an important position. What follows, it contains Z as a dense subring. The groups in Z are precisely the open subgroups of Z, and it is easy to verify that. It's really a finite index. Taking for each number, natural number, the prime factorization Chinese render theorem implies, the decompositions follows. Yes, and passing to the projective limit. Okay, we have this. This takes the natural embedding of Z into Z hat to the diagonal embedding. Okay, this is a good example. Actually, that's what we were looking for in the first section. Let's see how it is explained. For the field FP, finite field with Q elements, we get isomorph. This is what we know because what? Because FQ these are all the elements. Solve this equation. And why is explained here. By mapping the Frobenius automorphism to 1. So Frobenius is mapped to 1. Because this is a cyclic group. The scalar group is cyclic. Wow, that's why we have this. Do you understand? Of course, there needs some proof to show that this is cyclic, but once you see cyclic and you see Frobenius is a generator, then the bijection is obvious. You just have to check the order of Frobenius. It's n. It's reason to the power n, q, reason to the q squared power, and then reason to q's power is become identity. Actually, how can you say this? You have this, right? What is this? Yes, you're right. This is true, but moreover, so this is a characteristic Q, isn't it? So now my question is it? Is it? Of course, you can write it explicitly as by doing this, it doesn't really answer the question. I think a nice way is to I think we can look at the order. So, for example, actually we know this is n-dimensional FQ space, isn't it? As a vector space it is. Right? And one checks that sigma is FQ linear. Homomorphism from this vector space to itself. Actually, what we have to check is This is by definition. This is okay. This is a linear map, Q-linear map. And this is I should call it sigma. For Venice, sometimes actually phi is a better notation for Frobenius. Sorry, someone call it phi. So phi is surjective actually, because okay, so it's not clear because what we know is this is true, but we know why it's injective. Because this is the field, of course the domain. It is injective and also Q-linear homomorphism, so phi is surjective, just projective. So it's automorphism, nothing more than this. This is just telling that it's automorphism. Then I think we can simply say that this subgroup of automorphism generated by this Frobenius has order n. Because this is a splitting field of x cubed to the power n equals x. It means there are some element. There are qn elements, so which means all the roots are distinct. Which means that you cannot write it as this is not for any n less than n. This is not true. Because we know this is Qn, which is not the same as Qn. So it has order n, and we know the dimension. The dimension of this is n. Because as vector space is n dimensional vector space, so it must be the same. This is not a very direct proof. It's winding here and we're hiding something. Okay. And when we pass into the limit, we send the Frobenius automorphism to identity and then this projective limit. To say this, this is called topological generator. Actually, to say this more precisely, it is what? It is because you already have the Galois group for F, Q, and sorry, this is and we have the map inclusion, right? Let's go back to the projection. Yes. Okay. The sigma is left to 1. The Frobenius. Okay. So it's the same map. It's still mapping to the power of Q. Qth power. And this one goes to identity element. You see, this doesn't mean that it must be identity here. It can be equivalent element, right? But in this case, it is. Because this transition morphism is identity map. Some other examples we have, for example, nth root of unity, and you're adding it is to where zeta n is p nth root, nth root of unity. Nth root of unity. In this case, this cyclic group has more than one generator. You see, that's more than one generator. That's phi n generators. Of those, copram to n is a generator, and so the identity element when passing to the limit. So okay, that's really nice. And passing to the limit is it p star? What is the identity element? This is p star. May not be the identity element in each position, but it is the identity element. But it is the system of topological of generators of cyclic groups, of course. It should be the one equivalent to this. But this, that's by definition, it doesn't have to be identity on each one. It can be xi, xn in each position, but finally by some row 9xn equals 1. There is this n, right? This. Which sends the Frobenius automorphism to identity and the subgroup onto the dense subgroup Z. Given this, it is now clear in the example at the beginning of this chapter how we were able to construct an element which did not belong to Frobenius. In fact, looking at it with isomorphism, what we did amounted to writing down the element which does not belong to me. So we find an element, we constructed an element. We constructed an element. But it is not Frobenius. Okay. We're using this description. that is still left to show why Frobenius is not. Why this is not. How is this projection? It is piecewisely, yes. So this element actually corresponds to what? Corresponds to 0, 0, 0, then 1p, and then 0, 0, 0, 1p squared, 0, 0, 0, 1p cube. It's like this, and 0, 0, 0. It is this element. We're taking the vector limit, it becomes zp. Right, this position becomes 1p in zp. Why this cannot be a Frobenius? Because as a Frobenius you have to what? You have to, on each position you have to be 1. Right? So very nice proof. Okay. Many more examples you see. Okay, so this is what we discussed. Joining all the rules of unity. Okay, what we look at all the p rules of unity is this part that however is product of this. Okay, so let's recall how do we guide this is by the Chinese remainder theorem. You see, it's by Chinese remainder theorem. We have this, and then we take in the product being very interesting. Okay, that's what we wrote. As groups Zp and Z have additive special cases of the class of procyclic group. These are profinite groups G which topologically generated by a single element. Yes? G is the closure of the subgroup. The open subgroups of a procyclic group of the form Gn and Dgn is closed in the image of the continuous maps. So it's the index n if I'm not wrong. Finite because it contains finite group. Quotient group is finite. We didn't see the index, but it's finite because it contains the finite group. Yes, this is a finite group. At least this group contains or fix the n. For example, we know of course this has index n, right? So this has finite index and therefore equal to it. Conversely, if H is a subgroup of G with index n, then this is the conjugates. Every procyclic group G. Sorry, we should not say like this. We want to show that Gn defined in this way. So this is the definition for me. Gn is the image of the elements of G reason to nth power. And we claim that it is open. because we look at the quotient, we claim it's a finite index. We claim this is a finite group, this quotient. Why? Because we have a dense subgroup which is finite, and so this claim that this quotient group is this one. What is this? This is the power of Frobenius. We know the power of Frobenius is a dense subgroup of G. So when you do the quotient, it's dense subgroup of this quotient, and obviously this all the power of Frobenius when you modulo Gn. What is left is here because it's cyclic. Because the nth power is cancelled, so it's left with those ones. It's finite. So here is the Gn. Why this is true? Let's look at this. If this has index n, do you know it's a cyclic group? Actually, it's procyclic. When you do the quotient, it's of index n. This is a cyclic group. If it's a cyclic group, which means every element has order n, or maybe we don't even need it to be a cyclic group. What we claim is any element we reason to dense power. An element of G we reason to the p's power, nth power, in H. Okay, so this is order n. Yes, this, there is no problem if I say this is a cyclic because this is topological generator. And the element is the power of this topological generator when we do quotient. But anyway, this is clear. What we prove is this: G is an indexed n subgroup. So it's an open subgroup of index n is of this form. This form. Every procyclic group of G is a quotient group. In fact, if G is topological, is a closure of, then we have the for every n a surjective homomorphism just into the projective being used continuous rejection. So we're proving this is a quotient. We show there is a surjection. In this case, the problem is look at the procyclic group condition, the definition. These are profinite groups which are topologically generated by a single element. In this case, we don't know what is a single element. It may not be Frobenius, but by a single element. And we claim that all the profinite procyclic groups are quotient of Z hat. And if your topological generator is sigma, then this sigma is dense because you have the closure of this subgroup generated by the sigma. Well, what's our argument? Remainder true when we were imagining full forgiveness. This is it. We can describe all the open of the index n for a procyclic group G. They are a subgroup of the form. Il y a très bien abelian torsion group and the puncturing duo. Puncturing duo is a profinite group because one has abelian torsion group, finite subgroups, right? By inclusion, finite subgroups. No, sorry. It's just a collection, the union of all the finite subgroups. And this torsion means this is true. And usually when we say if A is p torsion, we can write. I think this is okay. If A is p torsion, we will have the inclusion. In this case, it's only torsion. You take the union. And hence, when we look at the whole, or can we rewrite this and maybe this is also inverse limit? Is it? So we have to define it for those have inclusion. It's inclusion for those who do not have inclusion. What is it? Yes, this is okay. I think for any AI, because for any AI AJ, there exists some K that both in it, right? For example, if a 2 torsion, which is 3 torsion, then we are all 6 torsion. Yeah, maybe this is okay, so we can take it in a minute. A final example, G is any group, and then Y is all normal subgroups. Finite index. It's called profinite completion. Okay, so we have some examples. We have a very general idea, but projective and inductive methods, like they are very nice examples, especially those working with Galois groups. Nice.